Launching into combat just 27 months after its maiden flight, the LTV A-7 Corsair II set a record for the fastest deployment of an aircraft into battle. Entering the fray in the mid-1960 SS as a rambunctious state-of-the-art attack aircraft for the U.S. Navy, it quickly proved its mettle in the skies of Vietnam, becoming the war's most successful tactical jet bomber. With a smaller size and less glamorous appearance than some of its flashier contemporaries, the A-7 would become affectionately known as the short little ugly fella or sell-off. Yet its unassuming visual profile belied its extraordinary capabilities, its pioneering use of a heads-up display, sophisticated digital navigation combat system, and computerized weapon aiming allowing for pinpoint accuracy and bomb delivery. Fundamentally altering the landscape of ground attack missions and setting a precedent for future generations of military aircraft. The A-7 Corsair II, renowned for its impressive range and endurance, mastered the skies with a payload capacity that seemed limitless. Equipped to deliver destruction with surgical precision, it handled a broad spectrum of missions, from laying sea mines and launching anti-ship strikes to executing armed interdictions and providing close air support. Celebrated as the ultimate bomb truck, the Corsair II was a powerhouse of versatility, capable of adapting to any combat scenario thrust upon it. In an era dominated by the quest for speed, the Corsair simply did what supersonics couldn't. In the early 1960s, as the pressures of the Cold War arms race demanded constant innovation, the United States Navy started looking into replacing the Douglas A-4 Skyhawk as its principal light attack aircraft. Although the A-4 would in fact stay in production until 1979 at the time, many believed its days were numbered and pushed for the creation of a more advanced attack platform that would fly at supersonic speeds, carry heavier payloads, and fly longer distances. In December 1962, the Sea-Based Airstrike Forces Study Group analyzed performance and cost for various aircraft concepts, scrutinizing 144 different hypothetical aircraft models before coming to a surprising but firm conclusion. A subsonic aircraft could outperform its supersonic counterparts. By opting out of supersonic speeds, the resulting aircraft design could be more compact, cost-effective, faster to develop, and simpler to produce, meaning more units could be made. Rather than focusing on velocity, the investigation suggested enhancing the precision of weapon delivery to minimize the cost of munitions per target. With these findings in mind, in May 1963, the Navy issued a requirement for a new type of aircraft, dubbed VL, an abbreviation of Heavier Than Air, Attack, Light. Keeping expenses in check, the Navy stipulated that all submissions should build upon existing aircraft models. This led major aviation players like Vought, Douglas Aircraft, Grumman, and North American Aviation to throw their hats into the ring, each beginning work on a new project based on one from their current roster. With the proposals submitted and the evaluation process complete on February 11, 1964, victory was awarded to Vaught's design, which drew inspiration from their highly successful F-8 Crusader. By March 19th, Vought had secured a Navy contract to start producing the initial series of what would become the A-7 aircraft, gaining the official name Corsair II the following year. This was a nod to Vaught's illustrious history of manufacturing aircraft bearing the Corsair name. While this stretched all the way back to their O-2U Corsair biplane of the 1920s and their SBU Corsair scout bomber from the 1930s, Vaught's latest design was intended as a successor to their legendary fighter bomber F-4U Corsair, which had stood out during World War II and the Korean War, establishing a direct lineage in its role as a ground attack aircraft. While the A-7 borrowed aesthetically from the F-8 Crusader, it also had some notable differences. Firstly, its body was shorter, measuring 46 feet, 1.5 inches, compared to the Crusader's 54 feet, 3 inches. It was also wider and had a more rounded nose, lending the aircraft a somewhat stubby appearance that led to its short little ugly fella nickname. With a span of 38 feet, 9 inches, the A-7's wings were not only around 3 feet broader than those of the Crusader, but they also had a gentler sweep. Both of these elements would contribute to better lift characteristics at lower speeds, enhancing the aircraft's maneuverability and control during such operations, as well as improving its loitering capability, allowing it to remain over the battlefield for extended periods. The Corsair used conventional ailerons located on the outer sections of the wing, providing more predictable roll control during low-altitude attack runs than the drooping ailerons used by the F-8. And the wings were also equipped with large slotted flaps on their inner sections, increasing their area and changing their camber. This improved the lift during takeoff and landing, particularly useful for operations from shorter runways or aircraft carriers, where enhanced low-speed lift is crucial. What's more, the wings could fold upwards thanks to a mechanism located between the flaps and ailerons, reducing the space required for storage and movement on crowded flight decks. The leading edge of the wing was stationary and featured a distinctive dogtooth design, which would help delay the onset of aerodynamic stall at high angles of attack, improving the wing's aerodynamic efficiency and control authority at low speeds and during high-G maneuvers, which are typical in attack and bombing runs. These wings were equipped with 6 pylons capable of carrying up to 15,000 pounds of a diverse array of weapons, including conventional bombs, guided missiles, and, later, precision-guided munitions, making the Corsair highly versatile and effective in various combat scenarios. As the A-7's design emphasized payload capacity and low-level bombing accuracy, it was decided to do away with the F-8's variable incidence wing mechanism in favor of a fixed wing which would support these requirements more directly. Like the Crusader, the Corsair had fully powered flight controls, meaning that the pilot's inputs to the control stick and rudder pedals were boosted by hydraulic systems, enhancing the aircraft's responsiveness and reducing pilot workload, especially important during high-speed flight and complex maneuvers. For improved aerodynamic braking, a large air brake was mounted on the aircraft's underside. The Corsair's landing gear, consisting of a 3-unit assembly, retracted into the body, with the front gear being a steerable twin-wheel setup designed to withstand the forces of catapult launches. Where the F-8 had used an afterburner-reliant Pratt & Whitney J57P28 turbojet engine, the A-7 was designed to operate at subsonic speeds, so an afterburner was not necessary. Instead, it was equipped with the Pratt & Whitney TF30P6 turbofan engine, which delivered 11,350 pounds of thrust and was also used in aircraft like the General Dynamics F111 Aardvark and early versions of the Grumman F-14 Tomcats. As the A-7 evolved, it transitioned to more advanced engines due to the original power plant's production challenges, compounded by high demand from both military and civilian sectors. These newer engines included the Pratt & Whitney TF-38 and the Allison TF-4102, a licensed version of the Rolls-Royce Spey engine known for addressing the early A-7 model's issues like compressor stalls and insufficient thrust. When it came to armament, apart from its sizable payload, the Corsair was originally fitted out with 2 cannons on the underside of its nose. In later versions, these were upgraded to a single, more powerful M61A1 Vulcan, a 6-barrel, air-cooled, electrically fired Gatling-style rotary cannon that could fire at an impressive rate, making it highly effective for strafing runs and air-to-air combat. The A-7 could also carry AIM-9 Sidewinders fire-and-forget missiles that could seek out the heat signature of enemy aircraft, making them highly effective in dogfight situations. These were mounted on both sides of its fuselage for rapid engagement with enemy aircraft. Understanding the risks posed by ground-based enemy fire, the A-7's design included significant protective measures. Its hydraulic systems for flight control were tripled, ensuring redundancy and reliability even under fire. Other critical systems were doubled for the same reason. Additionally, key areas of the fuselage were reinforced with armor, reducing the aircraft's vulnerability to damage and ensuring the pilot's safety during low-altitude operations. Yet the Corsair truly came into its own through its use of state-of-the-art systems. The AN/APQ-116 radar was designed especially for the A-7, while later versions upgraded to the AN/APQ-126, seamlessly integrated with the ILAS digital navigation system. This advanced radar setup was linked to an IBM navigation and weapons delivery computer, enabling the A-7 to drop bombs with high precision from increased distances. This capability significantly enhanced the aircraft's survivability, especially when compared to faster jets like the McDonnell Douglas F-4 Phantom II, which had to get closer to their targets for bomb delivery. A notable first for the A-7 was the inclusion of a modern head-up display, or HUD, crafted by Marconi Elliott. This HUD projected vital flight information such as dive angle, airspeed, altitude, drift, and the aiming reticule directly in the pilot's line of sight. This feature, now commonplace in military aircraft, was a significant innovation at the time. Another example of pioneering technology used by the Corsair was the Projected Map Display System, or PMDS. Providing a real-time projection of the aircraft's location over two different map scales greatly enhanced the pilot's navigational accuracy and situational awareness. The A-7 also boasted data link capabilities that enabled hands-off carrier landings, a feature made possible through its approach power compensator or auto throttle, streamlining the landing process and enhancing safety. Below the radar screen, pilots had access to an innovative projected map display, which was linked to the inertial navigation system. This display offered a detailed map, showing the aircraft's current location over standard navigation charts, providing unparalleled situational awareness. Additionally, the A-7's advanced inertial navigation system could autonomously navigate to up to 9 predefined waypoints, thanks to its integration with the all-axis autopilot. This hands-off flying capability reduced pilot workload and improved mission efficiency. The system's accuracy was top-notch, with minimal inertial drift in new models, and it could be updated through various means, including flyover, radar, and take-in updates, ensuring the aircraft's precise navigation and positioning throughout its missions. The A-7 took to the skies for the first time on September 27, 1965, with a swift and smooth flight test program. Despite some naval officials advocating for a slowdown to further enhance the A-7's avionics, the push to quickly deploy the aircraft prevailed as American involvement in Vietnam rapidly increased. By October 14, 1966, the Navy had received enough A-7s to establish the first squadron, which reached operational readiness by February 1, 1967, and entered combat in the Gulf of Tonkin by December that year, representing one of the shortest turnaround times from first flight to combat deployment of any aircraft in history. However, the Corsair's participation in the conflict was not limited to Navy use. Under pressure from the U.S. government and Army, who believed a subsonic aircraft like the A-7 would be best equipped to provide troops with air support, the U.S. Air Force ordered their own modified version in November 1965, designated A-7D, which would enter service from 1970. Impressed by the upgrade, the Navy responded with their own new version, the A-7E, gradually replacing their already existing A-7A, A-7B, and A-7C models in Vietnam. Throughout the war, the Corsair proved itself as a highly effective addition to both military branches, its precision strike capabilities allowing for more effective and efficient use of ordnance, reducing collateral damage and increasing mission success rates. In one particularly notable Navy mission on October 6, 1972, 4 A-7Cs from Attack Squadron 82 effectively dropped 8,000 pounds of high explosives on the Tan Hoa Bridge. 2 of the Corsairs were equipped with 22,000-pound walleye-guided bombs, while the other 2 carried 2,000 pounds of MK-84 general-purpose bombs. Their coordinated strike successfully hit and damaged the center piling on the bridge's west side, breaking it in half and causing its subsequent removal from the military's list of active targets. The following month, the Corsair would again be in the spotlight for actions near Tan Hoa, this time with the Air Force. On November 18, 1972, Major Colin A. Clark led a critical combat search and rescue mission in the area to save the crew of a downed Republic F-105 Thunder Chief. The operation extended over 8.8 hours, during which Major Clark and his wingman came under intense .50 caliber anti-aircraft fire. In recognition of his leadership and bravery in coordinating the successful rescue, Major Clark received the Air Force Cross, while his A-7D was later placed on permanent display at the National Museum of the United States Air Force, located at Wright-Patterson AFB in Ohio. The USAF A-7D completed 12,928 combat missions in the Vietnam War, suffering only 6 losses, one of the lowest rates of any American aircraft during the conflict. In terms of bomb delivery, the aircraft ranked second only to the Boeing B-52 Stratofortress for the total volume of ordnance dropped on Hanoi. It also achieved higher bombing accuracy and dropped more bombs per mission than any other U.S. attack aircraft. After the war, the Air Force initiated the process of transferring its active-duty A-7D aircraft to Air National Guard units. In 1989, A&G Corsair squadrons would expend 2,715 rounds of ordnance in the U.S. invasion of Panama, having been training with Army and Naval forces defending the Panama Canal. Meanwhile, the Navy held onto its A-7Es, and they would frequently participate in U.S. operations throughout the 1980s and early 90s, such as the invasion of Grenada, conflicts in Lebanon and Libya, and Operations Desert Shield and Desert Storm before the last fleet operational squadrons were finally retired in May 1991. The A&G retired their last Corsairs 2 years later. Elsewhere, however, the Corsair would continue to roam the skies, finding new homes in the air forces of Portugal, Greece, and Thailand, while a bid from Pakistan to buy 110 A-7S from the U.S. in 1976 was rejected for fears of intensifying their arms race with India. When Greece withdrew its final Corsairs from service in 2014, it marked the end of a 49-year career. The LTV A-7 Corsair II may not have been the fastest or most elegant bird in the sky, but its near half-century of service stands as a testament to its impressive versatility, survivability, and reliability. In aviation history, few aircraft capture the imagination quite like the de Havilland Sea Vixen. With its alien-like twin-boom design and offset cockpit, this British bird of prey looks like it flew straight out of a science fiction movie. But make no mistake, the Sea Vixen was very real, and it packed a punch that made it the terror of the skies during the Cold War. As the last all-British fighter to serve with the Royal Navy's Fleet Air Arm, it represented the pinnacle of British aerospace innovation, defending the nation's interests across the globe for over 2 decades. A fighter jet armed with cutting-edge missiles and able to intercept enemy bombers in pitch darkness or raging storms, the Sea Vixen was a true pilot's aircraft that pushed the boundaries of naval aviation. Its swept wings and powerful Rolls-Royce Avon engines propelled it to near-sonic speeds, while its advanced radar system gave it eyes that could pierce through the blackest night. But what truly set the Sea Vixen apart was its unconventional 2-man crew arrangement. While it presented unique challenges, its configuration allowed for unparalleled specialization in combat roles, making the Sea Vixen a fearsome predator. The origins of the Sea Vixen go back to 1946 when de Havilland began discussions with the British Admiralty about requirements for a future jet-powered, all-weather, radar-equipped fighter. These talks revealed several key requirements: a 2-man crew to handle the complex radar and navigation equipment, twin engines for safety over water, and swept wings for high-speed performance. In response, de Havilland began work on the DH-110 design in 1947. The project aimed to create a versatile platform capable of serving as an interceptor for the Royal Air Force and a fleet defense fighter for the Royal Navy. This dual-role approach was ambitious, seeking to create a single airframe that could meet the diverse needs of both services. The first DH-110 prototype, designated WG-236, incorporated several innovative design elements that would define the aircraft. At the heart of the DH-110 was its all-metal semi-monocoque structure, a significant departure from earlier de Havilland designs that used wood. This construction provided greater strength and durability, essential for withstanding the stresses of high-speed flight and carrier operations. The fuselage was divided into several sections, with the central portion housing the cockpit, fuel tanks, and engine bays. The DH-110 retained the twin-boom layout seen in de Havilland's earlier Vampire and Venom fighters, but with significant advancements. This configuration allowed for a shorter, more compact fuselage, highly beneficial for carrier operations. The booms extended rearward from the wing, supporting the tailplane and vertical stabilizers. Their structural rigidity and additional fuel storage were a critical factor in extending the aircraft's range and endurance. The wing design of the DH-110 was a key feature, incorporating a 45-degree sweep with a thickness-to-chord ratio of 10% at the root, tapering to 8% at the tip. This sweep angle was chosen as a compromise between high-speed performance and low-speed handling characteristics, essential for an aircraft expected to operate from carriers. For this same reason, the wings incorporated hydraulically powered ailerons and large split flaps. In the tail section, the twin-boom design supported a high-mounted tailplane, which reduced interference from wing vortices and engine exhaust. Initially, the tailplane was fixed, but later versions would incorporate an all-moving tailplane for improved control at transonic speeds, a modification that greatly enhanced the aircraft's high-speed handling characteristics. One of the most distinctive features of the DH-110 was its cockpit arrangement. The pilot's position was offset to the left, while the observer, who acted as radar operator and navigator, was housed in a compartment to the right entirely within the fuselage. This unusual configuration, which would later earn the nickname coal hole for the observer's position, provided the observer with a dark environment for better visibility of the radar screens. While innovative, this would later prove controversial due to outward visibility and safety concerns for the observer. Powering the DH-110 were two Rolls-Royce Avon RA, 3 turbojet engines, each capable of producing 6,500 pounds of force of thrust. These engines were housed in the central fuselage, with intakes on either side of the cockpit and exhausts beneath the tail booms. This twin-engine configuration provided the necessary power for high-speed flight and offered a measure of redundancy, characteristic of aircraft used in overwater operations. The landing gear of the prototype featured a conventional tricycle arrangement. The nose gear retracted forward into the fuselage, while the main gear retracted inward into the wing roots. This configuration would later be strengthened and modified to withstand the rigors of carrier operations. In terms of armament, the initial schematics called for 4 30mm Aden cannons housed in the lower fuselage beneath the cockpit. This potent armament was intended to give the DH-110 significant firepower against both air and surface targets. The aircraft was also designed to house an AI-18 radar system in the nose, providing all-weather interception capabilities, a critical feature for its intended role as an interceptor. The wing design of the DH-110 was a key feature, incorporating a 45-degree sweep with a thickness-to-chord ratio of 10% at the root, tapering to 8% at the tip. These enabled accurate long-range interception missions. For communications, the aircraft featured UHF and VHF radios, allowing for clear contact with ground controllers and other aircraft. On September 26, 1951, the DH-110 prototype took to the skies for its inaugural flight, initiating a rigorous period of testing and evaluation. Early flight tests demonstrated exceptional performance, with the aircraft achieving supersonic speeds in a shallow dive by April 1952. This accomplishment placed the DH-110 at the forefront of fighter technology. However, the promising start of the DH-110 program was marred by tragedy. On September 6, 1952, during a demonstration at the Farnborough Air Show, the first prototype disintegrated mid-flight, resulting in the loss of both crew members and 29 spectators. This catastrophic event led to a thorough investigation and subsequent redesign of the aircraft. The investigation revealed that the wing structure had failed due to oscillations induced by transonic airflow. In response, de Havilland implemented significant structural changes. The wings were substantially reinforced to withstand the stresses of high-speed flight. This included additional ribs and spars, as well as thickened skin in critical areas. A prominent wing fence was added to each wing, improving airflow characteristics and reducing the risk of sudden aerodynamic breakup at transonic speeds. One of the most significant changes was the replacement of the fixed tailplane with an all-moving surface. This modification provided better control authority at high speeds and improved the aircraft's ability to recover from high-speed stalls. The fuselage was also strengthened to improve overall structural integrity, particularly in the areas connecting the wing and tail booms to the central structure. These modifications delayed the program, but ultimately resulted in a more robust and reliable airframe. The second prototype, WG-240, incorporated these changes and resumed flight testing in June 1954. Despite the improvements, the RAF decided to abandon its interest in the DH-110, opting instead for the Gloucester Javelin. However, the Royal Navy remained interested in the design as a potential fleet defense fighter. As the Royal Navy showed interest in the DH-110, further modifications were made to create what would become the Sea Vixen. A complex hydraulic folding mechanism was introduced, allowing the outer sections of the wings to fold upwards for carrier storage. This ingenious system reduced the aircraft's wingspan from 51 feet to 31 feet when folded, a useful feature for maximizing storage space on crowded carrier decks. A robust arrestor hook was installed beneath the rear fuselage, enabling carrier operations. This hook could withstand the extreme forces experienced during arrested landings on carrier decks. The landing gear was also significantly reinforced and equipped with oleo-pneumatic shock absorbers to handle the stresses of carrier landings. The nose gear was fitted with a catapult sprag, a necessary addition for steam catapult launches from carrier decks. The AI-18 radar system was adapted for naval use, with additional maritime modes added for surface search and target identification. These enhancements made the Sea Vixen a more versatile platform, capable of both air defense and maritime strike missions. The production Sea Vixen FOW-1, an abbreviation of Fighter All-Weather Mark I, incorporated naval adaptations and featured several advancements over the prototype. The aircraft measured 55 feet 7 inches in length, with a wingspan of 51 feet and a height of 10 feet 9 inches. Its wing area totaled 648 square feet, providing ample lift for carrier operations. Empty, the Sea Vixen weighed 27,950 pounds, while its maximum takeoff weight reached 41,575 pounds, showcasing its significant payload capacity. Propulsion came from two Rolls-Royce Avon 208 turbojets, each producing 11,000 pounds of thrust. This powerful combination gave the Sea Vixen impressive performance figures. At sea level, it could reach a maximum speed of Mach 0.91, equivalent to 690 miles per hour, and climb at a rate of 9,000 feet per minute. The aircraft's service ceiling was 48,000 feet, allowing it to intercept high-altitude targets. On internal fuel alone, the Sea Vixen had a range of 790 miles, extendable through external drop tanks. The FOW-1 was intended to give the DH-110 significant firepower against both air and surface targets. The aircraft was also designed to house an AI-18 radar system in the nose, providing all-weather interception capabilities, a critical feature for its intended role as an interceptor. Several unique systems set the Sea Vixen apart. Its complex fuel system comprised multiple integral tanks in the wings and fuselage, with a total capacity of 1,100 imperial gallons. Dual independent hydraulic systems powered various aircraft functions, while electrical needs were met by a 115 VAC system with a ram air turbine for emergency power. The Sea Vixen's avionics suite was advanced for its time, centered around the improved AI-18 radar. This system provided search, track, and targeting capabilities with a range of approximately 30 nautical miles, effective against targets from sea level to 70,000 feet. An integrated weapons management system coordinated the radar, navigation systems, and weapons controls. Navigation capabilities were further enhanced with a tactical air navigation system, TACAN, improving the aircraft's ability to operate far from land-based navigational aids. The FOW-2 variant, introduced in 1964, brought significant improvements to the Sea Vixen design. The most noticeable change was the extension of the tail booms forward of the wing leading edge. This modification increased fuel capacity by 120 imperial gallons and provided space for additional electronic countermeasures equipment, enhancing both range and survivability. Armament on the FOW-2 was upgraded to include the more advanced Red Top air-to-air missiles. These second-generation missiles offered improved range, maneuverability, and kill probability compared to the earlier Firestreak, significantly boosting the Sea Vixen's air-to-air combat capabilities. The FOW-2's avionics saw substantial upgrades. An improved AI-18 radar system was installed, offering better detection and tracking capabilities. New electronic countermeasures equipment in the extended tail booms provided enhanced protection against radar-guided threats. The communications suite was also upgraded with a secure system for transmitting sensitive information during operations. Cockpit improvements were a key feature of the FOW-2. The observer's position received a larger, frangible perspex canopy, allowing for easier emergency egress. This addressed a major criticism of the original coal hole design. The pilot's canopy was modified to remove the central frame, improving visibility and situational awareness. Crew safety was further enhanced with the installation of Martin Baker Mech 6 ejection seats. These advanced seats provided improved survival chances in a wider range of emergency scenarios, including underwater ejection, a crucial feature for a carrier-based aircraft. These enhancements made the FOW-2 a more capable and survivable platform, better suited to the evolving threats of the Cold War era. The Sea Vixen served with the Fleet Air Arm from 1959 to 1972, playing a crucial role in Britain's naval air defense during a period of significant global tensions. Its advanced design and capabilities represented the pinnacle of British naval aviation technology in the early Cold War period, bridging the gap between the first generation of jet fighters and the more advanced multi-role combat aircraft that would follow. Throughout its career, the Sea Vixen participated in several operations, including the Kuwait Crisis of 1961 and the Indonesia-Malaysia confrontation from 1963 to 1966. These deployments demonstrated the aircraft's versatility and importance to Britain's global naval presence. However, the Sea Vixen's service was not without challenges. The aircraft had a relatively high accident rate, with 55 out of the 145 produced being lost in crashes. Many of these accidents were fatal, highlighting the inherent dangers of carrier-based aviation and some of the aircraft's design shortcomings, particularly the problematic observer's position in early models. The Sea Vixen's retirement in 1972 marked the end of an era for British naval aviation. It was replaced by the McDonnell Douglas Phantom FG-1, signaling a shift towards adopting American aircraft in the Royal Navy. After retirement, several Sea Vixens found new roles as target tugs and in weapons testing. Today, the legacy of the Sea Vixen lives on through preserved examples in museums across the United Kingdom, and the memories of those who flew and maintained this unique aircraft. Its distinctive design and advanced capabilities for its time ensure that the Sea Vixen remains an iconic symbol of British naval aviation history, representing a period of rapid technological advancement and the challenges of adapting jet aircraft to carrier operations. In the tense years following World War II, as the Cold War began to take shape, the United States found itself facing a new and unprecedented threat, the possibility of Soviet bombers penetrating American airspace. To counter this danger, the U.S. Army Air Force needed a new breed of aircraft, one capable of operating in all weather conditions day or night to intercept and destroy enemy bombers before they could reach their targets. Enter the Northrop F-89 Scorpion, a twin-engine all-weather interceptor that would become the backbone of U.S. air defense throughout much of the 1950s. Its distinctively elevated tail unit and high-mounted horizontal stabilizer gave it an almost alien appearance in the skies, a flying embodiment of the brave new world of Cold War aviation. But this unorthodox design was far more than an aesthetic choice. It was a fusion of aerodynamic innovation and tactical necessity, allowing the Scorpion to soar to stratospheric heights and reach blistering speeds. From its first flight in 1948 to its final mission in 1969, the F-89 would transform dramatically, from a conventional gun-armed fighter to a nuclear-capable interceptor. This constant evolution mirrored the escalating tensions of the Cold War itself, culminating in a weapon that could unleash the power of the atom from the edge of space, an airborne sentinel standing ready to face the ultimate doomsday scenario. In the aftermath of World War II, the global political landscape was rapidly shifting. The alliance between the United States and the Soviet Union, forged in the crucible of war, was quickly deteriorating into a state of mutual suspicion and hostility. As tensions rose, so did concerns about national security, particularly the threat of a surprise aerial attack. The United States Army Air Force, which would soon become the independent United States Air Force, recognized the need for a new type of aircraft to meet this emerging threat. The propeller-driven night fighters of World War II, such as the Northrop P-61 Black Widow, were no longer sufficient to counter the new generation of jet-powered bombers being developed by the Soviet Union. On August 28, 1945, the Army Air Force issued a specification for an all-weather fighter aircraft capable of fending off enemy bombers, even if they were to approach under the cover of darkness or in the midst of adverse conditions. It would need jet engines in order to be fast enough to catch up with jet-powered Soviet bombers and carry sufficient firepower to destroy them. It would also need to climb quickly to high altitudes, while incorporating the latest advancements in radar and fire control systems. In response to this specification, 8 aircraft manufacturers submitted proposals. Eventually, Northrop came out on top with their design, designated the N-24. Northrop's selection was influenced by their expertise in night fighter design, demonstrated by the successful P-61 Black Widow. The initial N-24 design was a sleek twin-engine aircraft with a slim fuselage and swept wings. This configuration was theoretically advantageous for high-speed flight, aligning with the Army Air Force's requirement for an interceptor capable of catching up with the latest jet bombers. However, as development progressed, this initial design would undergo significant changes. On June 13, 1946, the Army Air Force approved an initial contract for 2 prototype aircraft. These prototypes were designated XP-89, with the P standing for Pursuit in the designation system of the time. The original XP-89 prototype was a testament to Northrop's innovative approach to aircraft design. Every aspect of the aircraft was carefully considered to meet the challenging requirements set forth by the Army Air Force for an all-weather interceptor. The XP-89's most striking feature was its size, larger than typical for a fighter of its era. This generous scale was necessary to accommodate the complex radar and fire control systems required for all-weather interception, as well as to provide space for a 2-man crew. The cockpit featured a side-by-side seating arrangement for the pilot and radar operator, a configuration chosen to facilitate better communication during long, stressful intercept missions. In a significant departure from the initial N-24 design, the XP-89 featured straight wings instead of swept ones, providing better low-speed lift characteristics. The wings had an aspect ratio of 5.88 and a thickness-to-chord ratio of 9%. Utilizing a NECA 0009 64 airfoil section. This combination was selected for its low drag at high speeds and stability at low speeds. Perhaps the most distinctive feature of the XP-89 was its tail section. The horizontal stabilizer was mounted high on the vertical stabilizer, well above the exhaust of the jet engines. This unconventional configuration served 2 crucial purposes. It kept the horizontal stabilizer clear of the turbulent hot exhaust from the engines, and it provided the stabilizer with clean airflow, enhancing the aircraft's stability and control. This unique tail design would later inspire the aircraft's nickname, the Scorpion. Powering the XP-89 were 2 Allison J35A9 turbojet engines, each producing 3,750 pounds force of thrust. These engines were mounted in the lower fuselage with intakes on either side of the cockpit. The engine placement necessitated a unique landing gear configuration with unusually tall, thin, high-pressure tires for the main gear and dual wheels for the nose gear. The original armament plan for the XP-89 called for 4 20mm cannons mounted in a nose turret intended to provide the heavy firepower necessary to quickly destroy bomber aircraft. However, this configuration would later be changed based on testing results. The large nose section was also designed to incorporate advanced radar and fire control systems, although these were not fully installed in the first prototype. These systems were crucial for the aircraft's intended role as an all-weather interceptor, capable of detecting and engaging targets in conditions of poor visibility. On August 16, 1948, the first XP-89 prototype took to the skies from California's Muroc Army Airfield. Test pilot Fred C. Brecher reported that while the aircraft handled well, it lacked power. As testing progressed, Northrop addressed this issue by replacing the original engines with the more powerful J-35A-21, giving rise to the F-89A. This version also featured a refined armament configuration with 6 fixed forward-firing 20mm T-31 cannons. The Air Force, which had become independent from the Army in 1947, placed an initial order of 48 units in July 1949. But only 8 F-89s were built as it became apparent that further refinements were necessary. The testing process took a tragic turn on February 22, 1950, when the second prototype, now designated XF-89A, crashed during a test flight due to tail flutter issues, resulting in the loss of 1 crew member. This incident led to a comprehensive reevaluation of the aircraft's design. Northrop engineers conducted extensive tests and analyses, implementing several crucial modifications to resolve the flutter issue. These included adding a jet wake fairing at the bottom rear of the fuselage, external mass balances on the elevator, and exhaust deflectors on the fuselage. These improvements were incorporated into the F-89B, of which 40 were built. The F-89B, while still considered an evaluation model, featured upgraded avionics, including a new Lear F-5 autopilot and improved radar systems. These changes represented another step forward in the Scorpion's evolution, but the aircraft was still not considered fully combat-ready. Despite these ongoing developments, the F-89 Scorpion officially entered service with the United States Air Force in September 1950, with the 84th Fighter Interceptor Squadron being the first operational unit to receive the aircraft. However, the Scorpion's early service life was plagued by technical issues, leading to a high accident rate. In response to these challenges, Northrop continued to refine the design. The F-89C, introduced in 1951, featured upgraded J-35A-33 engines, each providing 5,600 pounds force of thrust. This significant increase in power addressed the performance issues identified in early testing. The aircraft also received retractable inlet screens to protect against foreign object damage to the engines. In 1952, a series of incidents involving structural failures of the wings led to the grounding of all F-89ES. Northrop addressed this issue by reinforcing the wing structure and adding fins to the wingtip fuel tanks to reduce aerodynamic stress. These modifications allowed the F-89 to return to service, but highlighted the ongoing challenges of developing and operating a cutting-edge interceptor. The F-89D entered service in 1954. This variant replaced the cannon armament with 104 Mighty Mouse FRs housed in large wingtip pods and featured a new Hughes E6 fire control system. In 1956, Project 6-Shooter led to the development of the F-89H, armed with 6 Hughes Falcon air-to-air missiles in addition to its rocket armament. The final and most potent version of the Scorpion was the F-89J. This variant, a modification of the F-89D, represented the pinnacle of the Scorpion's evolution and a significant leap in interceptor capabilities. The F-89J was specifically designed to carry and deploy a weapon that epitomized the tensions and technological arms race of the Cold War, the MB-1 Genie rocket with its nuclear warhead. The MB-1 Genie was an unguided air-to-air rocket with a W-25 nuclear warhead yielding an explosive force of 1.5 kilotons. To accommodate this powerful new armament, the F-89J underwent several modifications. The wingtip missile pods of the F-89D were replaced with 600-gallon fuel tanks. and underwing pylons were added to carry 2 Genie rockets. This configuration dramatically increased both the aircraft's range and its destructive capability. The F-89J's nuclear armament was a direct response to the perceived threat of Soviet bomber fleets. The idea was that a single nuclear-armed interceptor could potentially destroy an entire formation of enemy bombers, even if its aim was less than perfect. This concept reflected the strategic thinking of the time, where the threat of overwhelming nuclear retaliation was seen as a key deterrent against enemy aggression. On July 19, 1957, the F-89J etched its name in aviation history by becoming the first and only aircraft to fire a live nuclear air-to-air rocket. This event took place as part of Operation Plum Bob, a series of nuclear tests conducted at the Nevada test site. The mission, designated John, was designed to prove the feasibility of using nuclear weapons in air defense. That day, an F-89J took off from Yucca Flat, Nevada, piloted by Captain Eric William Hutchison, with Captain Alfred C. Barbie serving as radar operator. Their target was not an enemy bomber, but a payload of rockets carrying scientific instruments suspended from a balloon at an altitude of 18,500 feet. At 7 a.m., the F-89J fired the Genie rocket. 14 seconds later, it detonated, creating a brilliant fireball and the distinctive mushroom cloud associated with nuclear explosions. The test was a success, demonstrating that a nuclear-armed interceptor could effectively engage high-altitude targets. Remarkably, a group of 5 Air Force officers volunteered to stand directly underneath the blast to prove the weapon's safety for use over populated areas. While this display of bravado would be unthinkable today, it underscored the different attitudes and understanding of nuclear weapons at the time. The successful test of the Genie rocket marked a significant milestone in the F-89's career and in the history of aerial warfare. It represented the culmination of the aircraft's development from a conventional interceptor to a nuclear-armed defender. However, it also highlighted the extreme measures considered necessary during the height of the Cold War to ensure national security. In total, 350 F-89Ds were converted to the J configuration. These aircraft served with both the Air Defense Command and Air National Guard units until 1969, standing ready to defend against a bomber threat that thankfully never materialized. The F-89J's nuclear capability, while never used in combat, served as a powerful deterrent during one of the most tense periods of the Cold War. The F-89's service with the active duty Air Force began to wind down in the late 1950s as more advanced interceptors like the Convair F-102 Delta Dagger entered service. However, the Scorpion continued to serve with the Air National Guard until 1969. A testament to its versatility and effectiveness. The Northrop F-89 Scorpion, despite never seeing combat, left an indelible mark on the history of military aviation. As one of the United States' first jet-powered all-weather interceptors, it bridged the gap between the propeller-driven fighters of World War II and the supersonic interceptors of the late Cold War era. The Scorpion's legacy lies not just in its role as a deterrent during a critical period of the Cold War, but also in the technological advancements it pioneered. Its development pushed the boundaries of jet propulsion, radar technology, and weapon systems, paving the way for future generations of fighter aircraft. Today, while the F-89 no longer patrols the skies, several examples have been preserved in museums across the United States, including the National Museum of the United States Air Force in Dayton, Ohio, and the Pima Air and Space Museum in Tucson, Arizona.